The partition of unity is the mathematical mechanism that allows us to take local functions and stitch them together into a single continuous global function without jagged edges or sudden jumps. When you do calculus on a complex shape like this torus, you usually cannot define one coordinate system for the whole object. You work in localized coordinate patches instead. But when you try to integrate across the entire surface, you hit a problem. These patches overlap. If you simply add up the integrals from each patch, you end up double counting the data inside these flashing red intersection zones. We need a way to blend these local pieces together. Instead of rigidly cutting the patches at their edges, we want to transition between them, distributing the weight in the overlap zones so that exactly 100% of the data is counted, no more, no less. That smooth blending is exactly what a partition of unity provides. It serves as the bridge that connects local topological structure to global geometry. In Walter Rudin's Principles of Mathematical Analysis, the partition of unity is found in Chapter 10, which covers the integration of differential forms. Before we can use it to integrate, we have to unpack two pieces of terminology. On a 2D graph of a smooth bump function, the support is the bracketed interval on the x-axis, where the output is non-zero. Being subordinate to an open cover means the function stays strictly within this patch, flatlining at 0 everywhere outside it. Once you have a collection of these subordinate functions covering your space, the defining rule of the theorem is that at any given point, the sum of all these overlapping functions must equal exactly 1. This zero boundary property ensures our local functions act as contained agents. They manage their specific territory and fade out before they can interfere with distant patches. Rudin states that given a compact set K and an open cover, there exists a finite partition of unity subordinate to that cover. To prove this, we construct a smooth local function peeking inside one neighborhood on compact set K. Using K's compactness, we reduce an infinite number of these neighborhoods to a finite subcover, leaving overlapping functions that completely blanket the set. These functions are disorganized. What algebraic operation forces their varying heights to sum to exactly 1? We normalize them. By dividing each individual function by the sum of all functions at that point, their combined total snaps perfectly flat to 1. We can perform this division because the compact set K is fully covered by patches where at least one function is strictly positive, meaning the denominator is never 0. This construction allows us to write a global integral as a finite summation of local integrals. By weighting the local integrals with our normalized functions, the global calculation becomes a series of local ones. Because the functions sum to exactly 1, the global integral is accurately reconstructed from these local pieces, ensuring no information is lost and no data is double counted. A partition of unity is a finite collection of smooth, non-negative functions that sum exactly to 1 on a compact set. It allows for the seamless transition from local coordinate patches to global mathematical spaces without boundary overlap errors. While abstract, this construction is the foundation for differential geometry and functional analysis on complex surfaces. If you found this breakdown helpful, please like the video, subscribe to the channel, and hit the bell icon. We will be doing more deep dives into classic texts by Rudin, Kreisig, Dummett and Food, and others. Thanks for watching.